We can also do halogenation at the allylic position. And the rationale for the allylic being a good one to pull off, we have hydrogen here. To pull off this hydrogen, it would be 444 kilojoules per mole. For the allylic one, it's 364 kilojoules per mole. And for this one down here, it's 402. So we extract a hydrogen, which would form this radical. So if you had some radical here, and then we would get that radical right there. This can donate into here. We're going to form a new bond here and the radical here. So this is resonance stabilized. If we have the same compound with bromine, we would get a bromination at the allylic position. To avoid competing reactions, if you use Br2, you might get other products. And to avoid that completely, we can use NBS, and that supplies radical bromine molecules. So we have NBS, which is N-bromosuccinimide, and that has a Br on this nitrogen. Once you add light to that, it breaks up this bond. So you have N radical, and this one. This one is stabilized by resonance. So once this N radical forms and the Br radical forms, the Br can abstract that proton. Get this radical here. That radical can react with the Br that's in solution and have the halogen abstraction. Radical plus radical. So during propagation, new Br radicals can form, and that just keeps the chain reaction going. In this case, we had a symmetrical molecule. If you don't have a symmetrical molecule, we can actually get two different products. We can brominate at this position here, which is the allylic position. And that double bond stays intact. Or we can also brominate at the other carbon. And the way that that happens is we are going to form the radical at the allylic position. When that gets brominated, we get this product. But if you recall, this is resonance stabilized. So one electron can come here, the other comes here, and that one goes there. So the new bond has formed here. There's a radical there. That one can form a bond with the new Br and get to that product. So with an allylic reaction, we can get two different products if your double bond is not symmetric. So here we're going to predict the products that are obtained with methylene cyclohexane and NBS. So I'm going to draw the radical that will form. It'll form on the allylic position. So with the Br radical, we get that product here. And then the allylic radical is also resonance stabilized, so this electron can come here. That one goes there. And we get the Br there. So we're going to see a mixture of both of these products. If we're looking at atmospheric chemistry, ozone is created and destroyed in the upper atmosphere, You can see this blue region in the drawing here is where the hole in the ozone is. Ozone molecules absorb harmful UV. We can see this ozone can get broken down from light from the sun into oxygen and generate heat. So ozone molecules will absorb those harmful UV rays, and it can be recycled as heat as energy is released and then reform ozone again. Ozone depletion happens about 6% each year and is a serious health concern. The hole in the ozone is attributed to free radicals that interfere with the O3 recycling process in the atmosphere. So the compounds that are most destructive to the ozone layer include chlorofluorocarbons, or CFCs. So chloro, that can form a radical here and a chlorine radical. These radicals are stable enough to reach the upper atmosphere, and it forms the free radicals that interfere with the ozone recycling process. CFCs were used a long time ago in refrigerants, and when refrigerators were thrown away, these things made it into the atmosphere. So there's CFC substitutes that generally will decompose before reaching the ozone layer. So these are the ones here that are less stable, and these are the halogens that are used now to fight fires because it deprives the fires of oxygen. Autooxidation is another radical reaction that happens, and this is what happens when compounds react with molecular oxygen. So some compounds, such as ethers, diethyl ether, these are susceptible to autooxidation. These hydroperoxides can be very explosive. Diethyl ether should not be stored for long periods of time, and they should also be dated when they're used. If you have cumene or dimethyl ether that can react with oxygen, this forms cumene hydroperoxide, or this hydroperoxide here. If you see white crystals around an ether bottle, you want to gently close the hood and tell somebody and then walk out of the lab. We should get everybody out of the lab so that we don't have to worry about an explosion happening. You'll notice that things that can get auto-oxidized are stored in dark containers, so it's reactive with light. Ether is stored in actually a metal container, so it doesn't send out glass shrapnel. It's also stored in the dark so that it slows down the reaction. So in the absence of light, autooxidation is usually a very slow process. So vitamin bottles or extra virgin olive oil also are stored in dark containers because they're susceptible to being auto-oxidized. And if you did not know, your olive oil or extra virgin olive oil can go rancid under that process, so we should store it in a dark place. Triglycerides are important to a healthy diet, but that can also be auto-oxidized. Specifically, you might get an OOH group here, which makes it not good for your body. Foods with unsaturated fatty acids have a short shelf life unless preservatives are used. So you might start reading food labels for things that are processed and notice that butylated hydroxytoluene, or BHT, is added, or the BHA is added to enhance the shelf life of these foods. Preservatives can also undergo hydrogen abstraction to quench carbon radicals that form the first step of auto-oxidation. So this BHT that was added from the last slide, that can prevent thousands of these auto-oxidation reactions by stopping the chain reaction. Why is BHT so good at taking on free radicals? It has sterics and resonance on its side. Natural antioxidants include vitamin C and vitamin E. And you can think about which one is hydrophilic and hydrophobic. The one that has more oxygens is hydrophilic. This is a vitamin that if you get too much of it in your body, it can just be excreted through your urine. Vitamin E is hydrophobic. If you have too much vitamin E, that's not going to get excreted. It's going to stick into your fat cells. So you don't want to have too much vitamin E. So back all the way in Chapter 9 when we looked at different alkene reactions, we had HBr plus an alkene giving us the Markovnikov product. And when we added HBr in the presence of a peroxide, that gave us the anti-Markovnikov product. So now you will see how this reaction actually works. We have OR, the ORs. This is going to be a homolytic cleavage. Form two OR radicals. That's 151 kilojoules per mole reaction. We're then going to get a hydrogen abstraction. new bond, new radical. So this is a fairly low activation energy, and so this is why this bromine can form the radical. And then we're going to do an addition reaction to the alkene. And that forms the most stable radical here. This is an H abstraction. So we get a new hydrogen adding here, plus Br radical. Delta H equals negative 25 kilojoules per mole for that one. So in this we get the product and then another bromine radical, which can then get terminated. We form Br. This is the coupling reaction. So the Br radical will react in order to give the more stable carbon radical, which was why the Br adds to the less substituted side. So we can also use free radical conditions to form polymers. A polymer has many small units called monomers that are put together in a long chain. Ethylene can undergo polymerization to form polyethylene. So there's CH2 units here that are repeating. In the radical polymerization reaction, we have an OR with this carbon radical here that can add to an alkene, and that will form another radical, which keeps propagating, and you form polymer that eventually gets terminated by destroying two radicals. In this one particular here, this is an end-to-end reaction, where the reaction just keeps adding on to the end of the prior radical. We can also get branching. In this case, this radical is going to branch off of there when the ethylene adds, and you get this branch. Branching makes polymer materials more flexible, just like a polyethylene squeeze bottle. Something like this 5-gallon bucket would have minimal branching. So the structure is very rigid. The caps of the bottles would be less branched, and the bottle squeezing part is more branched. There's different, more popular varieties of polymers. This one comes from propylene. To make polypropylene, this you might see in carpet fibers, in different appliances or car tires. Styrene makes polystyrene, which you might have included in televisions, radios, or styrofoam. Vinyl chloride, or PVC, is used in piping for plumbing. It has been used for CDs, if you remember what a CD is. Garden hoses, raincoats, shower curtains. PVC has a lot of different applications. And tetrafluoroethylene is in Teflon, which is used for nonstick coating for frying pans. There's lots of uses for halogenation and synthesis. You can use radical chlorination and bromination in different types of settings. If you look at this here, there's no functional groups. If you wanted to do a reaction with this, there's no alkenes or alkynes that we can do reactions with. But if we want to brominate the most substituted position, this now gives us a functional group handle. The same thing with chlorine. If there's only one type of proton available in the whole thing, you can use chlorination. But that one is a difficult one to control because it can react with many things. So in a synthesis reaction, if you're trying to target something that doesn't start with a functional group, you want to be able to add a functional group to that. This methyl cyclohexane, we add NBS to give us a functional group handle. You can do a substitution then, or you can do an elimination, and then there's other possibilities of reactions from the elimination. So if you wanted to propose a synthesis here, we're making our observations. We've added 2 carbons and an alkene. So if we look at this currently in its state, there's no functional group here, so I want to put one in. I can use Br2 plus light. That will give me a Br there. I can do an elimination. This is where I'm making my disconnect. So I need to add these 2 carbons here. And the easiest way to do that is to do this from an alkyne. So if I'm going to do a quick retrosynthesis here, I'm looking at making Br plus this. So these 2 carbons come from those 2 carbons. And if I can make this an acetylide, I can attack that and then do the reduction. So if I want to make this bromine, I'm going to use HBr, ROOR. So I get that Br, and then I'm going to start with my acetylene, NaNH2, NH3. So that will form my acetylide. Then I add this to it. I get that, and then I can use H2 Lindlar to get the final product.